Thank you, everyone. Welcome. Today, same as we did yesterday, we are going to play one video, or we are going to carry on with the video we were watching yesterday. This is going to be the first part of the lecture today about GPU. This will take about 1 hour. And after that, I will introduce you to GPU programming. Maybe some of you are already familiar. It will be good to have a review, and for others it will be maybe a new interesting thing. The lecture, the video recording, the link to the video recording that we are going to watch now is there, as you see in the slide. Don't hesitate to ask any questions. You just raise your hand and we will answer your questions.
Okay, so GPUs are SIMD engines underneath. You've actually seen all of the principles except for the integration of the principles. The instruction pipeline operates like a SIMD pipeline, like an array processor. However, you have not seen something, which is the programming. The programming is done using threads, not SIMD instructions. That's why GPUs have taken off a lot, whereas vector processors have been very specialized to high-performance computing. So to understand this, we should go back to our parallelizable or vectorizable code example. By the way, if I say vectorizable, it's the same thing as parallelizable. People use these interchangeably. But first, we need to distinguish between two things. One is the programming model, which is a software, and the other is the execution model in hardware. And we've seen the distinction a little bit earlier, but let me clarify that a little bit. So the programming model refers to how the programmer expresses the code or views the machine, right? And we've seen sequential, von Neumann model. We've seen the SIMD model, data parallel. We've seen the data flow model. If the programmer is expressing things as those data flow graphs, that's their programming model. We haven't seen as much the multi-threaded model, but we've talked about it, right? You basically have different threads having different program counters and executing separate pieces of code. And I'll introduce the term SPMD in a little bit. Execution model, on the other hand, refers to how the hardware actually takes that code and executes it underneath. And these don't need to be the same. For example, we've seen out-of-order execution, which took sequential piece of code and executed in out-of-order, right? Vector processors, array processors, data flow, multiprocessors. We've seen multi-threaded processors, fine-grained multi-threading, right? You have multiple threads, multiple program counters, multiple register files, and you do multi-threading in hardware. And these two things could be very different. Execution model can be very different from the programming model. And this is one example that we've seen very well. A GPU, it turns out, is an SPMD model, very close to multi-threaded. It's really a multi-threaded model implemented by a SIMD processor underneath. And we'll see what those things are. Basically, you have multiple threads, but a GPU dynamically combines them into vector-like instructions. So let's look at these different, this example a little bit. This is the example that we had, scalar sequential code. We're going to look at how to do it sequentially, which is not so interesting, how to do it data parallel, and how to do it in a multi-threaded fashion, which will be the newer part. So this is the sequential code, and it looks like this, basically. You need a branch, of course, but I'm going to ignore that for now. This can be executed on a pipeline processor. You've seen out-of-order execution processor. That's also you've seen. Basically, independent instructions are executed when ready. If you have an out-of-order processor, basically different iterations can be in the pipeline at the same time, right? This load may take a long time. And this add and store may depend on it, so they'll need to wait in the reservation stations. But these instructions can execute, right, in an out-of-order processor, because this is from a different iteration. They're independent. And they can execute in parallel. And basically, how good an out-of-order processor will be on this code is dependent on how long your latencies are. Because if your latencies are only one, out-of-order processor doesn't buy you much performance, actually any performance in this code. And second, how far ahead the out-of-order processor can look, how big its reservation stations, how big its instruction window is. So if this load takes 500 cycles, the out-of-order processor can look ahead 500 instructions. Basically, it can cover 500 divided by 4 iterations, right? Ignoring the branch again. And it can find the instructions from that later iteration at the very bottom and then execute them in parallel with the load that's still waiting waiting its data. So that's the beauty of out-of-order execution. You can look ahead in the sequential code and execute. In other words, basically, if you think about this a little bit, the loop is dynamically unrolled by the hardware. How many of you know about loop unrolling? Okay, some of you. I don't think you should have seen it in any class. Basically, loop unrolling is a compiler optimization where the compiler takes the iterations and combines them. It takes multiple iterations and combines them into a single large iteration to eliminate the branch. So if you know that this loop is going to iterate 1,000,000 times, to get rid of the branch, you unroll it and put together, I don't know, maybe 500 iterations together. That way you reduce the branches in the code. You have one branch every 500 iterations instead of one branch every iteration. Right? An out-of-order processor does something very similar, basically. It looks ahead and it basically sees many iterations inside the machine and finds independent instructions. So a superscalar processor can take this and can fetch and execute multiple instructions per cycle, right? So if you have out-of-order superscalar, now you can do more, right? A superscalar processor basically doesn't need long latencies. It can execute multiple instructions per cycle. As a result, it can improve performance. But basically, we've seen that this code can be executed in a superscalar manner by fetching and executing multiple instructions per cycle also. And VLIW, we've also seen the compiler can somehow pack these instructions, independent instructions, together and execute them in a VLIW manner. So, for example, a smart compiler can pack these loads from independent iterations together into a VLIW instruction, right? So you have, if your width is 8 wide, you can have an 8 wide load. But you have 8 loads in the VLIW instruction. That's the difference from SIMD. Right? Instead of having a single load that says you do it 8 times on 8 different data elements, you can pack these 8 different loads from 8 iterations into a single VLIW instruction, except your instruction would be really long, really large. But you can also pack other things together. The VLIW compiler can say, oh, I want to pack this add and, well, I cannot do the add and store. I want to pack this add over here with the load over here. There's no reason you cannot do that because they're independent of each other. Okay, so basically we saw a lot of techniques to improve the sequential execution model. The programming model is sequential, but if you look at this, the execution model is very different. Okay, so let's look at the data parallel programming model. Data parallel programming model, somebody needs to take the scalar code and realize each iteration is independent and reorder the operations such that it looks like this. Basically, the programmer or compiler generates a SIMD instruction to execute the same instruction from all iterations across different data. This should really be called operation in this case, because it used to be instructions in the scalar model, but we're going to take these operations that are doing exactly the same thing, pack them into a single SIMD instruction. And that's what we did earlier. So this is called a vector instruction, basically. And vectorized code looks like this. You have a vector load. You're loading from a base address array into V1. You're loading B into V2. You're doing a vector add, and you're doing a vector store. So that's beautiful. And this is the programming model. Basically, your program looks like this. And think about the execution model. Like, what does the hardware do? This is really best executed by a SIMD processor, a vector or an array processor. If you take this beautiful piece of code and execute it on a pipelined in-order processor, you're really doing no justice to someone who's done a lot of work to optimize a program, right? You could, right? There's no reason why you cannot take this code and translate it into an in-order pipelined, or even not pipelined, processor, right? Remember, you can always take the code and turn it into a single scalar instruction at a time and execute it, not to have multiple functional units. That's the beauty of architecture. You have this code, software at the top, you have this hardware and you can do anything in between to make the hardware really simple, or to make the software really simple, by doing translation, right? But somebody went through a lot of pains to execute this code. Why would you actually reduce it to execute on a really simple in-order processor? That makes no sense. So this is really best executed by a SIMD processor. Okay, so let's look at the third programming model. This is multi-threaded. Basically, I've already given you the idea. You need to, again, realize each iteration is independent over here, and you turn the iterations into different threads. So the programmer or compiler generates a thread to execute each iteration, and each thread does the same thing, but on different data, in this case. So I'm going to assume that programmer takes only one iteration and makes it a thread. Now you can say that, oh, that's too short. Why don't we pack together 10 iterations, and then that's a thread? That's true, and that's also done, but I'm not going to simplify the explanation, I'm going to assume one iteration is a thread for the rest of this talk. So this can be executed on a MIMD machine. MIMD, remember, multiple instruction, multiple data. Basically, multiple threads. This could be executed on one processor. This could be executed on another processor, on another processor, another processor. Now you parallelize your code on a multiprocessor, which we have not talked about as much, but the concept is very simple. You have multiple processors. Or, well, what is a MIMD machine? It could also be executed on the fine-grained multi-threaded machine that we've discussed, right? These are all independent of each other. So you have multiple threads in the fine-grained multi-threading. Remember, multiple program counters, multiple register files in a pipeline machine. Every cycle you fetch from a different thread until you finish all the threads. That's also a MIMD machine. So you actually have seen MIMD machines. Fine-grained multi-thread machine is really a multiple instruction, multiple data machine because it executes multiple instruction streams. So a thread is also called an instruction stream, if you will. Okay, so this programming model actually has a particular name. Multi-thread is very general. In this case, the realization is that each thread is doing exactly the same thing. It's exactly the same code, right? There's no difference between threads. They're executing exactly the same code. So this particular model is called single program, multiple data. Basically, if you look at each thread, it's really the same program, but you're really operating on different data elements with that program. This is operating on the data elements that belong to the first iteration. This is operating on data elements that belong to the second iteration, zeroth elements, first elements, second elements, third elements, ... So that's what the single program multiple data. Sometimes you may see single procedure multiple data also over here. You can call it single thread multiple data also. So this the realization is that, the GPU realization is that this can be executed on a SIMD machine, basically. You can take this single program, multiple data, multi-threaded program, and design a much more efficient machine than a multiprocessor. A multiprocessor replicates many processors, so it's not very efficient. But GPU says, oh, my hardware is going to be very SIMD-like, single instruction, multiple data-like, so I'm going to take this programming model and execute it on a much more efficient machine. That's why GPUs are, if your code looks like this, you'd better execute on a GPU and not a multiprocessor because you'll waste a lot of efficiency on a multiprocessor. Whereas in a GPU, it's going to combine those things into vector instructions. So basically, GPUs, they're SIMD machines, but they're also called SIMT machines. I'll have to give you the terminology because you may see this later on. It's also called single instruction multiple thread. Basically, you have multiple threads, but you combine the same instruction from those threads into a single instruction and execute it on parallel functional units that do exactly that instruction. So we'll see that. So basically, a GPU is a SIMD machine, except it's not programmed using SIMD instructions, as I've just said. It's programmed using threads with that SPMD programming model. Each thread executes the same code, but operates on a different piece of data. And each thread has its own context. This is obvious. It can be treated, restarted, executed independently. It has a different program counter. It has a different context, basically, different registers. But we will see why this is useful. This is useful, actually, because you can move the threads to different places, right? You can decide, oh, I know that iteration 1 through, I don't know, let's say 16. Let's say you have 16 parallel function units. I know I have 16 parallel function units. One way I can do execution is I'm going to combine 16 iterations, consecutive iterations together and execute them together. But you can really pick any thread from any iteration and put them together because they're all independent. Okay, this will be clear soon. So let me define you more terminology. Basically, a set of threads executing the same instruction is dynamically grouped into a warp or wavefront. Warp is the NVIDIA terminology. Wavefront is the AMD terminology by the hardware. And we'll see an example of this. A warp basically is a SIMD operation formed by hardware. I'll give you, actually, go back here. So this is your multi-thread model. You have these loads that are exactly the same thing, right? It's the same load operating on different data elements. So we're going to combine these into a warp, let's say 16 of them, or 32 of them. And we're going to treat them as a single entity, except each operation will operate on a different data element, but it will look like a SIMD instruction, SIMD operation. Okay, so warp, remember, it's a set of threads that execute the same instruction. They're all at the same program counter over here. Okay, we already talked about this. So let's look at how a warp is formed by the GPU. Basically, a GPU takes these warps. This is an example of a warp. You have warp 0 at program counter X. That means you have multiple iterations, multiple threads inside that warp, and each of them are doing the same loads, but on different data elements. Makes sense, hopefully. So this is warp 0. So when you can fetch this, you can fetch from this load, which means that you'll be fetching multiple loads. And then the next instruction you fetch from this warp will be the instruction that's at PC X plus 1. And then when it's done, you fetch from the next instruction. And then when it's done, you fetch from the next instruction. Make sense? Basically, it's like SIMD instructions, but there is no vector code over here. You still program with loads, adds, and stores, except you indicate that they're warps, and you keep fetching from these warps. So let's look at it in more detail. Any questions so far? This is hopefully clear, right? Yes?
Why is it useful? It seems to me that it's not much more difficult to just program it as a SIMD
SIMD. Okay, that's a very good question. Well, let's defer the answer in a little bit, because threads are easier to deal with from the programmer side, and SIMD is not very flexible. That's one of the main reasons. But we'll get to it toward the end. Let's understand the model first. Basically, in SIMD, a single sequential instruction stream, you have a single sequential instruction stream of SIMD instructions, right? It's sequential. So you will see that, actually. Maybe we'll start that. Each instruction specifies multiple data inputs. So you have vector load, vector add, and vector store, and you need a vector length. Basically, we're going to eliminate that vector length over here. If you think about SIMD, it's data parallel, but it's instruction sequential, right? There's no concept of threads in there. So you're limited by sequential execution in the end. We eliminated that sequential execution. That's one of the answers to your question. There are multiple answers. And the second is programmer now needs to deal with this vector length. GPUs can make it a little bit more flexible. So SIMT, on the other hand, multiple instruction streams, single instruction, multiple thread. You have multiple instruction streams of scalar instructions. First of all, you don't need to think about vectors. You can think scalarly. You will need to think about arrays still. But threads are grouped dynamically into warps. So what you have is really scalar instructions, nothing different from your existing single instruction, single data programming model, but you specify a number of threads that you operate on. And depending on how the GPUs actually expose this to the programmer, you may need to specify the warps also, but let's not get into that. I think there are some inefficiencies in existing systems for that. Does that make sense? So I think, let me answer part of your question to begin with. This is inherently a little bit more sequential, whereas here you have many, many threads, so you have more flexibility. And the second is, this is a bit easier to program because it's not different from writing a single sequential program, right? You don't need to think about vectors and vector length. And vector length actually causes some other issues in the machine. If you need to change the vector length, you'll need to stall the pipeline, if you remember that we've discussed before. Yes?
But it does add overhead, right? The hardware needs to
Yeah. So if the programmer specifies that, it doesn't add that much overhead. Right. But if you want to do fancy things, yeah, you need more overhead, yes. Okay, so there are two advantages. Basically, you can treat each thread separately, aside from what we've discussed. You can execute each thread independently on any type of scalar pipeline. So this leads to MIMD processing. And we'll see examples of this. And you can group threads into warps flexibly. Basically, you can group threads that are supposed to truly execute the same instruction underneath in hardware. This is a bit harder to grasp. We will see this a little bit more. But let's take a look at this one first. Yes?
What exactly is the difference again between a SIMD instruction and a scalar instruction?
A SIMD instruction, basically, it's inherently a vector instruction. You have a length. You basically do a vector load. You operate on vector length number of elements. A scalar instruction is just one element, one pair of elements. Make sense? So, for example, let's go back to here. Okay. So you do a load, you load one piece of element, one element. Whereas here, you do a vector load, you load vector length elements. Okay. So let's look at the multi-threading of warps. Basically, assume that we have a warp that consists of 32 threads, which means that you have 32 threads that are executing this program. And 32, a warp, if you remember, let's go back actually over here. It's a set of threads that execute the same instruction, right? They're at the same program counter. So we're going to synchronize them together. Basically, you have 32 threads, 32 instructions that are at the same load over here. Now, how do if you have 32,000 iterations over here and a warp, so warp is really a hardware construct in the GPU. A GPU says, I can execute these 32 threads at the same time at the same program counter. But you may have many, many more iterations than 32, right? So if you have 32,000 iterations and you want to partition your program such that you execute one iteration per thread, you really have 1,000 warps in the end. And assume that those 1,000 warps can be in the machine at the same time. And these warps can be interleaved on the same pipeline. This is, remember, fine-grained multi-threading. Let's finish this because we want to get to a good point over here. But basically, you can interleave these warps on the same pipeline. You can do fine-grained multi-threading of warps. So let's take a look. Let's say this is your warp 0 at program counter X. You have 32 of these iterations bundled into it. And you fetch this one. In the next cycle, you fetch warp 1 at program counter X. The next iterations. In the next cycle, you can fetch warp 2. In the next cycle, we can fetch warp 3. In the next cycle, you can fetch warp 4, ... Right? Basically, you're multi-threading across this granularity of the warps. Now, you can also have warp 20 at PC X plus 2 executing somewhere in the machine also, right? And that's basically, you can calculate what iteration it's executing. It's really executing this iteration, 20, because we have 32 warps. You really have 641. This is the 641st iteration over here. Or maybe I started with iteration 1, so I ignored iteration 0, so that's fine. So this is correct. Basically, you can have many warps in the machine, and they can be interleaved together. A GPU interleaves them in a fine-grained manner. So let's look at this again. So you have these scalar threads. We've grouped them together such that they have a common PC. So this is a warp. And remember, again, a set of threads that execute the same instruction is called a thread warp. It's SIMT. And again, SIMT is not a very common term. NVIDIA uses that, but some other companies may not use it. All threads run to the same code. And you have many of these thread warps inside the machine. So now this is looking like a multi-threaded machine, fine-grained multi-threaded machine, right? Except it's fine-grained multi-threading across the warps. So you may have lots of warps over here, and you push one into the pipeline every cycle. You fetch from this warp, and then the next warp, and then the next warp, and then the next warp. Now you may ask, what's a warp? Like, why is it called a warp? Basically, the threads that run lengthwise in a woven fabric, if you go to the dictionary definition of a warp. Somebody wanted to play with the word threads. Basically, you have multiple threads that are running lengthwise, and it's basically a woven fabric together that are put together. Okay, let me see. Actually, let's go a little bit more. Basically, It's called a shader core also. You don't need to know all of this terminology over here, but a GPU core is called a shader core because of graphics reasons. And it looks like this. Basically, you have program counter, mask. Remember the mask? That's, we'll see that later on. This is basically a warp. And you have many warps. And every cycle, you send one of the warps to fetch from the iCache. And that warp gets decoded and executes on the scalar pipeline, but executes basically on different data elements. So we will see that this looks like vector lanes. And then once the warp is done, it goes back to this queue such that it can get executed in the next instruction. You can now fetch the next instruction from that warp. In the meantime, once this warp is basically once this warp has moved to decode stage, you can fetch another warp. And then once this warp has moved to its pipeline, you can fetch another. The next warp you fetched moves to the decode, and you can fetch another warp. So basically, you're really multi-threading across the warps that you fetch. And each warp is really multiple threads grouped together into a single single program counter. They're at the same program counter, but you operate on different pieces of data. So hopefully this is clear. Okay, so this is another view of it. It's a little bit more detailed, if you will. So why this is, you have these warps available for scheduling here, and this is the SIMD pipeline over here. But each lane is what we've seen earlier, basically. So why is it fine-grained multi-threading? Because you have one instruction per thread at the pipeline at a time. So there's no interlocking. That was the benefit of multi-threading. And you interleave this warp execution to hide latencies. So remember, a long time ago, I showed you the heterogeneous element processor. And it had these queues. There was a fetch queue. It had these threads waiting in the fetch queue. Now we have these threads, but again, threads are grouped into warps. And then if a thread gets a cache miss, for example, if it needs to wait for memory for 1,000 cycles, you take out that warp, move it into this waiting queue, and it sits in this waiting queue for a while until it gets its data, and it moves back into the pipeline after it's done, after it gets its data. So basically, we're treating things at the granularity of a warp, and we're scheduling things at the granularity of a warp also. You're fetching at the granularity of a warp, and you're waiting at the granularity of a warp. And this is nice because these threads are taken out of the pipeline. They're waiting over here. Hopefully, there are many, many other warps that are coming into the pipeline that can hide the latency. Right? And you see the register file over here. This enables long latency tolerance because, again, in graphics, you have millions of pixels. Right? Remember, if we're doing the same code that we've seen in MMX, you have this, it was, I think, 7 instruction length code. Each thread does 7 instructions, but you have millions of pixels. If you assume that a warp is 32 threads, you divide a picture that has millions of pixels into warps of 32. So you have 1,000,000 divided by 32 warps. So your latency tolerance is really huge. Even if one warp waits for 1,000 cycles, you have thousands of other warps that are coming into the machine. Right? Okay, let me finish this also, I guess. So recall this slide. Basically, if you have a 32-thread warp executing an add, inside the machine, you could actually do something like this, right? You could actually have a vector machine that looks like this. But you could also do this. You can have 4 functional units and executes 4 of the threads of a warp at the same time. So remember, if you have a 32-thread warp, you have 32 threads, 32 data elements. You can do each of them every cycle. This is the first element, first thread, second thread, third thread, fourth thread, fifth thread, ... This is like a vector processor underneath. Or you could do much more like a GPU. You could do 4 of the threads of a warp at a given time, and then the next 4, and then the next 4, and the next 4, and the next 4. And these execute on lanes that look like this. So we've seen exactly the same thing before, except instead of having a vector registers, we have registers for different thread IDs. So we have partitioned our register file. This lane over here has registers for threads 0, 4, 8, ... This lane over here has registers for threads 1, 5, 9, ... It's beautiful. Right? Okay, I'll finish with this slide, I think. And then we can take a long break, and then we can come back. Basically, again, let's take a look at this example. You've seen this before. We can overlap execution of multiple instructions. An example machine that has 32 threads per warp and 8 lanes, which means that every cycle we issue 8 threads from a warp. We can complete 24 operations per cycle while issuing 1 warp per cycle. So basically, this is the first warp, warp 0. It's executing this load unit. So you basically send it in the first cycle, 8 of these threads. In the next cycle, the next 8 threads. In the next cycle, the next 8 threads, ... So you have 8 lanes in your machine. In the next cycle, you fetch from a different warp, because we're doing fine-grained multi-threading. And in the next 4 cycles, we're going to send the threads, the 32 threads, from this warp. In the next cycle, you fetch from a different warp. In the next cycle, you fetch from a different warp, different warp, different warp. So if you overlay this picture with the SIMD machine, you'll get exactly the same thing. Right? Except these are called warps over here now instead of vector load, vector multiply, vector add. Okay. Let's stop here. Let's take a 15-minute break and come back at 14:23.
Exactly. In modern GPUs, let's say a typical number of shader cores is 16, and in each of them, you can have at each particular cycle, you can be scheduling 1 warp instruction, one of these instructions, or even more, because you might have more than 1 warp scheduler. So each warp means that you are scheduling 1 instruction. Okay? Warp 0, warp 1, warp 2 is when you schedule 1 instruction. The width of this instruction is the number of threads that are running concurrently, is the warp size. In this example, but in real GPUs, it's 32 or 64. Okay? And then this is the number of cycles that each of these instructions take. No, actually it's not. Not in this case, sorry. In this case, you have the 32 threads per warp and 8 lanes. As you can see, because this is inspired in the oldest CUDA architecture. So in the oldest CUDA architecture, you needed 4 cycles to schedule the entire warp. Lane means each of the vector units. Okay. We will go back on this later. And actually, you will see. I have a slide for this architecture and also for a newer architecture, and you will see what's the difference, because sometimes, so in the oldest NVIDIA CUDA architecture, you have 8 lanes in each shader core, and later you have more. So we will get back on this. Okay? Any other questions? Okay, let's continue with the video.
There you are. All right, it's already 23, so let's get started. So I want to go over this picture one more time because I kind of rushed it a little bit. Even though you've seen this picture before, it's a little bit different here. Basically, this picture builds upon this picture over here. So here we have a warp that has 32 threads. You're basically executing the same instruction across 32 threads or 32 pieces of data elements. They're doing 32 different iterations, right? Now, if you have only one functional unit that looks like this, you execute them in 32 cycles, right? That's this example. If you have 4 functional units, you execute 4 of the threads in a warp in one cycle, and then the next 4, and then the next 4, and then the next 4, and then the next 4. Now your performance has increased. You can finish this entire warp in 8 cycles because you have 32 threads per warp, and you're doing 4 threads per cycle. Threads equals iterations in this case, right? And this picture is exactly the same as what you've seen in the SIMD instruction earlier. This is a vector add, right? So if you had 32 functional units, then you would execute all 32 iterations or 32 threads in one cycle, right? So the reason you have, basically somebody needs to determine how many functional units you have, and that's the hardware. And you may specify some number of threads per warp, and in that case, that gets executed in different number of cycles depending on the hardware you execute on. So if one GPU, for example, may have, hopefully not one, but 4 functional units per lane, or 4 functional units or 4 lanes. In that case, in that GPU, a 32-thread warp will take 8 cycles to execute. Another GPU may have 32 lanes or 32 functional units. In that case, that same warp would take only 1 cycle to execute. Right? Okay? And this is the lane as we've seen before. So to best understand this, you should really overlay this with the SIMD lecture that we had. So here we're assuming we have 32 threads per warp, but 8 lanes. Which means that we can start 1 warp per cycle, but that warp is going to finish in 4 cycles in the load unit, right? Basically, for example, at time t0 over here, we'll start warp 0. This is 1 cycle over here. In the first cycle, you'll finish 8 of the threads. In the next cycle, you'll finish this next 8. In the next cycle, you'll finish that next 8. In the next cycle, you'll finish that next 8. Now, the warp is done with all 32 threads. Now what happens is you increment the program counter and you move to the next instruction in this warp. And remember the next instruction, you're doing a load, another load, and then add. What was it? It's an add, I think, and a store. Yes. That was our thread. Load, load, add, store. So this load, once this load is done, the next warp will go, the same warp will go to the next load. Once that load is done, the same warp will go to the next add. Once that add is done, the same warp will go to, I guess here we don't have a store unit, but to the store unit, right? Yes?
Maybe I missed it, but why do we put more than 8 threads per warp?
Yeah, so that's, we didn't go into the programming model as much, but somebody needs to specify the number of warps. And the question is, who does it? In current cases, it's really the programmer specifies it. But there is really no reason for the programmer to fully specify it. But why would it be higher? Because again, it's a contract between the software and the hardware. The software says, "Oh, I have 32 warps," but then the machine may have a small number or a big number. So it's usually good to have it a larger number, such that the machine can have more flexibility in executing it with the number of functional units it has. Hardware, yes.
Hardware, I could just do 32 threads and it would split it over 4.
Exactly, yes. So there are other trade-offs, but let's not go into that. You're right, absolutely. If the warping is completely done by hardware, you can match the warp to the number of units you have. But there may be other reasons like control overheads. Let's not go into that because you may need to identify the warps in terms of, you may have state that's dependent on the number of warps you have. And that may be a limited state. And you may want to put many, many threads into that. So that's one reason, for example. And that's actually the reason why you have more threads more warps, more threads per warp than lanes in a GPU. Okay, so basically, at the end of 4 cycles in the load unit, this warp finishes and it goes to the next instruction. So while this warp is executing in its first cycle in the load unit, now some other warp, completely independent, is being decoded over here and starts execution in the multiply unit in the next cycle, right? That's the pipeline machine, basically. It's completely independent because it's executing completely different 32 iterations over here. And then it takes also 4 units. Of course, you can extend this in terms of how long it really takes, how long the multiply unit takes. We're going to assume that multiply unit takes actually 1 cycle. You basically start 1 instruction per cycle, and at the end you get the result. So at the same time, this warp is executing its first 8 iterations, or 8 threads. This add is being decoded, and then next cycle, it basically gets dispatched into the add unit. So that's how you get to execution. And once this load unit becomes free, another warp that's executing a load instruction can get scheduled onto this, that's being decoded, can get dispatched into this load unit. So it's really pipelining and parallelism at the same time. Makes sense, hopefully. So if you remember this picture from the SIMD lecture, these were really called vector loads, right? And vector add, vector multiplies. Okay, so let's look at the memory access a little bit. Basically, this should be obvious by now, but basically, same instruction in different threads access different data elements. So how do they figure out which data elements they access? They basically use a thread ID to index memory and access different data elements. So in this case, we have 16 threads over here, and we have 16 data elements from one array, let's say. You can extend this to the other array that you're loading. If you have 4 threads per warp, we can have 4 warps over here. And warp 0 looks like this, basically. You have threads 0 through 3, and they need to access memory locations 0 through 3. So you index the array with the thread ID. Right? In this case, location happens to be 0. So basically, the memory address of a given warp is calculated as the base address of the array plus the thread ID, because that's how you grouped the instructions into threads. Each thread operates on a single data element. Make sense? That's pretty simple. Now, I'm not going to go through this, but this is just to show you the example over here. So this is a CPU code. And this is kind of the GPU code. You can ignore the thread ID. There's a way of calculating the thread ID, depending on how you block your program and constitute the threads. But basically, your code looks very similar if you look at this, right? It's essentially CTID equals AATID plus BBTID. And this may not be the exact way the GPUs are programmed today, but this is a good simplified example in CUDA, some version of CUDA. Make sense? So basically, this is exactly like you would program if you would think, if you think. There's no vector instructions here. It's just a little bit more management added to your sequential code. And there are many threads over here. That's why you need to somehow figure out the thread ID over there. So this is another sample GPU program. Again, you don't need to know this, but this is a little bit less simplified. I'll just point out that you basically, this exactly is the same, right? But if you really want to learn it, you should take probably a different class or learn it on your own. Okay, so let's wrap it a little bit. Basically, we're looking at warp-based SIMD versus traditional SIMD. So what are the differences? So traditional SIMD contains a single thread. And this was in answer to your question earlier. You have sequential instruction execution, and you have lockstep operations in a SIMD instruction. So if you have a vector load and you're loading from 64 elements, if they happen to be in different, if one of them happens to get a cache miss, one of them happens to take too long, that's too bad. You need to wait for all of them to finish until you move to the next vector instruction, right? So this is the lockstep part. This is similar to the VLIW, if you remember. In VLIW, you had multiple operations. If one of them took long, all of the operations needed to wait because the execution model is really sequential. And programming model in this case is SIMD. There is no extra thread. Software needs to know the vector length. In a sense, you're encoding the parallelism in the vector length, not in the threads. And ISA contains vector or SIMD instructions. So warp-based SIMD, or GPU SIMT model, consists of multiple scalar threads executing in a SIMD manner. Basically, the same instructions executed by all threads. Doesn't have to be lockstep. So you can actually merge these threads in different ways. For example, if a GPU recognizes that this thread is executing at the same program counter as this thread, maybe it can merge them. Right? Of course, this requires hardware complexity, but it's possible to do it. And each thread, because each thread can be treated individually, right? Meaning that it can be placed in a different warp. So programming model is really not SIMD. And software doesn't need to know the vector length because there is no vector in the end. So this enables multi-threading, and this enables flexible dynamic grouping of threads. We've talked about multi-threading, and we're going to talk a little bit more about this dynamic grouping. But the ISA is scalar in the end. Each operation, each instruction operates on scalar values. And SIMD operations are formed dynamically. So as you've seen, essentially it's SPMD, single procedure, single program, multiple data programming model implemented on SIMD hardware. Okay, so let's look at SPMD a little bit more. This is, again, single procedure, program, multiple data. Just to make sure this is a programming model. It's not a computer organization, right? Each processing element executes the same procedure except on different data elements. That's each thread, maybe I should not call it a processing element over here, but each thread executes the same procedure. And procedures can synchronize at certain points in the program. Remember the barriers that we've discussed a long time ago? But you don't need to know exactly how to do this programming. Essentially, you have multiple instruction streams that execute the same program. Right? So just to make sure this is written over here, you have each program or procedure that works on different data, and you can execute a different control flow path. So you've seen the different data part really well, but they can also execute a different control flow path. So how do you support that? Let's see. And many scientific applications are programmed this way. You've seen array addition, for example, matrix multiplication. You can basically express it in this single program, multiple data programming model. And many scientific processors are actually running things on MIMD hardware. GPUs are essentially program things in a similar way, except they run on SIMD hardware, as we've seen. Okay, so let's look into this part. We've covered all of this over here, SIMD, SIMT. And we've seen that you can treat each thread separately. Let's look at grouping threads into warps flexibly. So this is actually some advanced things GPUs do, but hopefully you'll see some similarities. So let's say you have a thread that's supposed to execute this thing over here. And it can have a conditional control flow instruction, right? In this case, you see one control flow over here and a bunch of branches because things are and a loop branch over here. So just imagine these things as instructions over here. You have an instruction and then determine which instruction to go to next. Another instruction, determine which instruction to go to next, and then do some stuff. And then your control flow basically looks like this. So each thread has these instructions, and threads can execute different control flow paths. So for example, one thread can take this path depending on the data value, because it's operating on array element 0. Another thread can take this path, because this if condition may not be evaluating to be taken to C, it may be evaluating to be taken to D. Another thread may be executing this path, another thread may be executing this path. We don't know where they execute, of course, until we execute the threads. But assume that we've grouped these threads into a warp, because you have, let's say, 4 iterations grouped into a warp. These threads will start executing, and while they're executing, we'll figure out that the next program counter, well, even here, after we execute this instruction A over here in this warp, we will figure out that the next program counter of the first 3 threads, I think it's first 3, yeah. First 3 threads should be B, and the next 3 threads should be F. Now the beauty is gone, right? Because these threads start out at the same program counter, but 3 of them want to go here, and 1 of them wants to go here. So how do you do that execution now? They're clearly not operating in the same instruction anymore. Yes? Exactly. So that's kind of what's done, except it's a hardware no-op, and you've seen this before. So let's take a look at this. Basically, this is called branch divergence. But I'll give you the solution. But no-op, when you said it says software no-op, you cannot do software no-op because they all need to execute the instructions, right? So this is the problem with grouping threads, right? They all, as long as it's sequential, they go through the same program counter sequence. But once you have a control flow, you have this problem that the threads that are grouped together are diverging from each other. This is called branch divergence. And this is why GPUs are not very good at irregular code. This is called irregular code. It's not a single piece of code where every thread does exactly the same instruction and there's no control flow. You have some irregularity based on the data that you process. You need to take different paths. We'll handle this, but it will come at the cost of some performance. So branch divergence occurs when threads inside warps branch to different execution paths. So let's look at, let's say we have 1, 2, 3, 4, 8 threads over here. We execute that instruction. The next instruction is a branch. That's good. We have 8 threads. We execute the branch. We figure out some of the threads want to go to path A, some of the threads want to go to path B after executing this instruction. So what does a GPU do? A GPU basically creates 2 warps. The first warp does the threads that need to execute path A. The second warp does the threads, or executes the threads that need to execute path B. And when they come together, when the next instruction is the same, the GPU merges them back dynamically. Now, we're not going to go into the hardware of how to do this. There's complicated hardware and GPUs to make sure this works. But you've seen this idea before at the vector machine. What was it called? Yes, exactly. It's vector masking, masked operations. So basically what the GPU does is after you finish this branch, GPU figures out a mask. It's called an active mask, actually. It says, oh, the next set of threads should execute path A, should have mask bits set. And those are threads 0, 2, 3, 7. Just based on the condition of the branch, where the threads need to go. And the threads that need to execute path B, the mask bits are for threads 1, I don't know, 4, 5, 6. Right. So you basically set the mask bits such that even though you're executing, you're sending all of those to execute on this instruction, only some of those will take effect. And the ones that will take effect are determined by the condition of the branch. And we call this predication, right? Predicated execution. Basically, the GPU has a predicate inside. Except GPU does it underneath. The programmer doesn't need to deal with this at all, right? The programmer just writes in threads and hopes that the program gets executed correctly. GPU groups these threads together into a common program counter and makes sure what the programmer expects gets realized by doing this. So this is how a GPU does branching. If you look at the vector machine, as a programmer, we needed to do masking, right? I needed to, for example, over here, show you how you generate the mask and how you complement the mask and you execute the other path. That's what we did. We created a mask over here, and some of the vector add instructions, let's say over here, were masked. And then we complemented the mask, and some of the vector add instructions got masked over here. And then we set the mask all to 1 again. So the GPU is doing all of that in hardware without requiring the programmer to do that. Again, all the programmer does is this. Write this code, except in the code form, not in this box form. Okay, so it's beautiful, basically. Same as conditional, predicated, or masked execution. And some of you recall this. That's good. So now you realize if you look over here, what's happening is only 50% of your machine is utilized at that particular point. You're doing an add. You have 8 lanes, but you're using only 4 of your lanes. So your efficiency of your lanes is really only 50%. So what if only 1 thread went here? your efficiency would be 1 out of 8. Now, if your machine has 64 lanes, only one thread takes the branch, your efficiency is 1 out of 64. Now, quickly your efficiency degrades. You have this hugely parallel machine, but you're underutilizing it. This is called SIMD utilization. What fraction of the execution unit is kept busy with a useful operation? So can we do better than this? So let me give you an example. So if you have many threads, you can actually find individual threads that are at the same program counter and group them together into a single warp dynamically when you need it, and then break the warp later on if needed again. So this reduces divergence, improves SIMD utilization, what I just discussed. SIMD utilization is a fraction of SIMD lanes executing a useful operation, executing an active thread. Yes?
The data it operates on can only be the one in the array, right? It can't do like... So everything has to be combinational circuits inside of the... inside of one thread, right? Else you couldn't dynamically warp them together with something else.
What do you mean everything has to be combinational? So you need to ensure that the thread can its data correctly, yes.
So it can't have any state apart from the state inside the array.
Exactly, yes. Exactly, yes. So basically, the state consists of the program counter, which is going to be awfully equal for these things that you're grouping, and the register file. Now, the register file is inside the machine, so that's okay. You just need to be able to access the register file correctly. So you need to be in the correct lane, basically. That's right, yes. Exactly. Okay, so let's take a look at an example of this. Basically, this is called dynamic warp merging or formation. You dynamically merge threads executing the same instruction and form new warps that are from warps that are already waiting. Remember, we have lots of warps in the machine. Some of them are at some PCs, some of them are at other PCs. Now, if you figure out that, oh, my new warp needs to be at this PC, but I have only 5 threads active out of 32, maybe you find some other warps that have 5 other threads active, and you merge them together. Now you combine them. Now you have a much better utilized machine. So enough threads branching to each path enables the creation of full new warps, basically. So let's look at an example. You have warp X, warp Y, and warp Z. We're going to combine these. So it happens that this warp X has these threads active. Active meaning they have mask bits set to 1 after a branch. And this warp has these other threads that are active. You can combine them to be a more full warp, assuming they're at the same program counter, of course. And that's how we combine them, right? Does that make sense? Now these warps, these threads will get their data correctly because this is executing in this lane, this is executing in this lane. And remember the lane structure that we had over here? We'll have to go really quickly back to this picture. Where is it? Okay, there you go. So you have registers for thread ID 0, 4, 8, and here, and 159 here, 2, 6, 10 over here, ... So you need to ensure that the lanes of the warps are preserved. The lane of the thread is preserved because it's going into that location, lane, where the registers are located. So basically, you can combine these warps. If you look over here, it's not as perfect, right? Here, what happens is you have these warps that are active, and you want to combine them with this other warp, these threads that are active, the blue ones. These orange ones are also masked. They have their mask bits set to 1, so they're active. Now, how do you combine these two? You can fill in the blanks over here, but you cannot fill in the parts that have blue because you already have a thread over there. Right? So you've combined this. You added some more threads to this warp, but some remain over here. Make sense? Now, the good thing is maybe there's some other warp that will fill in this part, so you'll get 100% utilization over here, and maybe you'll fill this in with some other ones. So hopefully you'll reduce the number of warps, amount of waste that you have in your execution units. Okay, which is this hope over here. So if you have another warp that looks like this, now what you can do is, you can do that, right? So you merge 3 warps into 2 warps over here, assuming they're at the same program counter, executing the same instruction. Sounds wonderful, right? It's like filling in the blanks, basically, so that you can maximize the utilization of your machine. It's amazing that existing GPUs do this. It's some hardware, but they do it. Okay, let's look at an example. This is a I'll go through the same thing just to emphasize it. Basically, this is this warp going into the branch, and it takes path A. Now, it so happens that you have another warp over here going into path A also. You can merge these things together. That's exactly how this happens in the previous slide over here. Yeah. Okay, you can study this. And I'm not sure if I have time to go over all of this, but if you actually take these slides and animate it, you'll see a nice picture over here of this exact full code where things get merged. And I'll recommend that you do that on your own and see how things behave. By the way, these bits over here, you basically here what we have is you have warp X and warp Y. They all start at the same point. And this is the mask bits. At this point, all threads in the warp are executing the same instruction, executing that instruction. But warp X, only the first 3 threads are executing instruction at B, and the other one goes to F. And warp Y, only the last 2 threads are executing the instruction at B, and the other 2 go to F. So if you actually animate this, you will see that you can create many warps over here in this example, toy example. So for example, over here, you can merge this thread B with another one over here, but then this one gets underutilized. But now you can merge things in the C and you eliminate one cycle. So if you do all of this, you will see that you complete the program much faster. But I'll leave you to do this. This is just fun. The basic concept, you can group threads at the same program.
This is supposed to be hardware managed, but this is just a research proposal. I don't think so.
Program counter together. That's it. Right? That's the basic concept. The rest is basically how do you design the hardware to make it efficient, which we're not going into over here. And it's a beautiful, a very powerful concept. So think about how to do this in a SIMD machine. Can you do it? No, right? Because in a SIMD machine, a vector load specifies those operations to be very tightly coupled. You cannot take out this operation from a SIMD instruction and move it to some other operation. Here, we don't have the SIMD, single instruction model. We have threads. A thread is decoupled from the other thread. You're just grouping them or ungrouping them dynamically. That's why this is much more powerful, in my opinion, than a traditional SIMD machine. Of course, it has its overheads. It's powerful in the sense that you can do these combinations so you can get higher performance potentially. With every idea, of course, there's a downside, so you can guess what's the efficiency of the SIMD machine. SIMD machine doesn't need to deal with the threads, right? So there's no overhead of this thread management in a SIMD machine. You have a single thread. So there are always downsides and upsides of an idea. Okay, so I think I've given you this, but I'll leave you with that question over here. Can you move any thread flexibly to any lane? And the answer should be no. Even if you had an empty spot in a warp. And another, okay, let me see if I have an example over here. I should have an example, right? Yeah, there you go. Actually, that is good. Yeah, this one. So here there's an empty lane over here. This thread is in this lane. Can we move it over here? No, right? Because it requires data from the register file that's here. Because remember, we partitioned the register file into lanes. You cannot move it over here, because when you move it over here, it will go to a register file, and it will get the wrong value. Because only registers that are belonging to threads that were assigned to this lane are here. And you cannot get your data from there. Now, it turns out you could, but with a lot of additional complexity, which we're not going to go into that. Okay. Question? Okay. So I think I've given you these slides, so I'm going to skip that and cover one more concept, systolic arrays. Any questions before that? How many of you find this fascinating, by the way? Okay, good. I have a lot of hands. How many of you wouldn't even care about this? That's okay. You can. Okay, I see 2 hands, but they sound like jokes. Yeah, I find this fascinating because there's a lot of complexity in this, but there's a lot of beauty also, I think, in the processing model. So it's always good to think about, like, why have GPUs been so successful today? And the programming model and the flexibility, everything we talked about has enabled them to be very successful. It's not clear if they will keep going to be that successful, because they're still at heart or internally a SIMD machine, right? They cannot do this difficult out-of-order execution at the moment. So if they really want to, if you want a GPU to really conquer the world and execute all kinds of programs, you will need to find a way of enabling it to extract this hard parallelism. It's still a machine that extracts relatively easy parallelism, right? It works really well if a lot of your data is parallel, and also you have thread parallelism. But it's not clear if it will work really well if those conditions are not fully true. Okay, so you've seen these slides before. Right? You can go back and look at them. But let's do.
Okay, I think we can start with the second part of the lecture. As I told you today, we are going to talk about GPU programming, or GPGPU programming. GPGPU means general purpose GPU. So it's using the GPU, which were traditionally designed for graphics processing, for general purpose computation. Sometimes you will find this concept of GPGPU. Other times you will see GPU computing, simply GPU computing. So this is the outline of what we are going to see. I don't know what's wrong here. But this is what we are going to see. What we are going to start looking at is what we can call the traditional accelerator model, in which we have the CPU on one side, the GPU on the other side, and in the middle we have some kind of bus that connects them, typically PCI Express bus. Okay. The last part, if we have time, we will take a look at two new programming features that are dynamic parallelism and collaborative computing. Several features that allow us to have like a more tight collaboration between CPU and GPU, and they can even access and modify the same data elements at the same time. I don't think we will have time to go through this today, but just in case, we have that in the slides. So this first part about the traditional accelerator model is going to be divided into essentially three main sections. In the very first section, we will see how the computation is organized. You will see that somehow we are going to review all the concepts that have been explained in the previous part of the lecture, but now the focus will be more on how to program the GPU to take advantage of these features or these capabilities. So we will first see how the program is organized, and we will talk about what is called the bulk synchronous programming model. Then we will see what's the memory hierarchy in current GPUs and how this memory is managed. And finally, we will talk about performance considerations. So, and a brief explanation of some optimization techniques that can be useful for really take advantage of the resources of the GPU and dealing with these, some of these problems that we have previously seen, such as, for example, the branch divergence that most likely I will call here intra-warp divergence, but it's exactly the same. So probably we can go very quickly over the first slides because you already know how the somehow the GPUs have revolutionized high-performance computing in the last decade. But as we saw in the previous lectures, this is not for free because this requires a new programming model and this entails new challenges. And we are going to talk today about these challenges a little bit. So it's not simply using the same code and pushing the play button and start executing or C code or C++ code on the GPU. This requires a much more complex transformation. So that's why the slide says that algorithms need to be re-implemented and rethought. And as it was pointed out in the previous part of the presentation, the programmer really needs to take care about the underlying hardware if he or she really wants to obtain the maximum performance that is possible from the GPU hardware. But the good thing is that there are many workloads that exhibit this massive data parallelism. They are inherently parallelizable. So, for example, computation on matrices, dense matrices, computation in image processing, they can easily take advantage of the GPU capabilities. Is what we call data parallelism. But not always. I mean, they're step-by-step GPUs are, the GPU programming model and the GPU architecture is evolving, and it's step-by-step also being better for the execution of more irregular workloads. We will probably see some examples of this. But the most important thing, and actually what we are going to talk more about in this part of the lecture, is the two main bottlenecks. The first of them is inherent and is impossible to skip, especially in the traditional CPU plus GPU system with the PCI Express bus in the middle, is that we need to perform data transfers from the CPU memory to the GPU memory. We are going to talk about main memory of the CPU, and the GPU memory, we will call it device memory or simply global memory. So every time I talk about global memory, I'm talking about the GPU memory. And also the access to this GPU memory, because as you already know, the technology has been evolving much faster for the computation units than for the memories. And same as DRAM, you already know that is a main bottleneck in current systems, as Professor Mutlu has explained in previous lectures. It's also an important bottleneck in GPUs. No matter that some of the newer GPUs are already using 3D stacked DRAM, like the recent NVIDIA Pascal or NVIDIA Volta architectures already use HBM2, but still we have a bottleneck there. You're also familiar with this. The main difference between CPU and GPU is in CPU we have very few but very powerful out of order cores. On the GPUs we have many weak but many in order cores. So it's essentially the main difference is what are we employing our die area on. In CPUs, we have these out-of-order cores, and we have very big caches. On the GPU, we essentially have a lot of small cores that we are going to call probably stream processors or CUDA cores. Okay, it's whenever you see each of these green squares, this is each of the vector lanes, each of the vector functional units that we have inside one shader core. We will see a better picture later. So this is what I call the traditional accelerator model. is assuming that we have one CPU on one side, GPU on the other side, and in the middle we have a PCI Express bus. We need to perform 3 operations if we want to use the GPU. The first of this operation, or the first step, is transferring all the input data to the GPU memory. So that's what we see here. From the CPU memory, we have to transfer, in this case, this matrix to the GPU memory. The second step is launching a GPU kernel, which is the function that is going to be executed on the GPU, and operate on this input data. And when we finish, we transfer the results from the GPU memory to the CPU memory back. We will see how these data transfers are programmed. We will see the instructions that we need to use just in a minute. But first, let's take a look at what's the organization that the kernel execution has. Because as of now, we have been talking about many threads, and we know that these threads are going to be executed on the shader cores, and actually you already know that these threads are organized into collections of 32 threads that are called warps or wavefronts, and they are going to be executed in parallel on the vector units or the streaming processors. But how should the programmer write that? The warp is a concept that is transparent for the programmer. The programmer only has to care about threads and how to arrange these threads into what are called thread blocks, or simply blocks. This is going to be the traditional program structure. We still have, in any application, might have sequential, non-parallelizable parts of the code, or modestly parallel parts of the code that maybe we can run on a multi-core processor using 2, using 4 CPU threads. But this is not worth offloading to the GPU, of course. And then we are going to have massively parallel sections that we want to execute on the GPU. So the traditional program structure can be something similar to what you see in the slide. We will first have one, for example, in this case, one CPU thread running some sequential code. When this thread finishes this part of the computation, we can also talk about that SysD, or sequential phase. We will offload part of the computation. We launch a kernel onto the GPU. And this kernel, actually this is the syntax to launch a kernel. And this kernel will make use of a certain number of threads. How are these threads organized? They are organized into thread blocks. And as you see, in the kernel launch, we have to define the execution configuration, which is the number of blocks and the number of threads per block. The entire collection of thread blocks that we are launching onto the GPU is called a grid. So we have a grid of blocks of threads. Where are the warps? The warps doesn't exist from the programmer point of view. I mean, if you want to be a skilled programmer, obviously you need to take care of the warps, and I will tell you where the warp exactly is. But in principle, you don't write your code indexing warps or something like that. So obviously, each of these blocks has the same number of threads. Okay. So when one kernel finishes, the control returns to the CPU. Maybe the CPU thread needs to still run some more parallel code, some more sequential code, and then launch a new kernel, maybe the same kernel or maybe a different one, a different function, which, by the way, can have the same number of thread blocks, the same number of thread per block, or different, okay? Of course, you already can figure out what's going to be a typical number of the threads per block. Any idea? Usually, we're going to use a multiple of the warp size. Okay? You will see why in just in a couple of minutes. So from the programming point of view, this is what we saw in the previous part of the lecture, that this is called the SIMD or the SPMD model. And we say that this way of programming is bulk synchronous. Why is it bulk synchronous? Because we don't have the ability to synchronize these thread blocks in an arbitrary way. The only way to synchronize these thread blocks is to terminate one kernel. There might be some fancy ways of doing that, but in principle, in the CUDA and in the OpenCL programming model, it only, if we want to synchronize different thread blocks, we need to terminate with a kernel and launch a new kernel. So that's what we call coarse-grained synchronization. However, it's true that within a thread block, it's going to be more flexible. Within a thread block, it's going to be possible to synchronize these threads that are within the same thread block without terminating the kernel. For this reason, we have a special synchronization instruction that you will see soon. So, as I said before, we are going to organize our kernel into a grid of blocks of threads. What you have here in parentheses is the name for the same thing in OpenCL programming model. It's AMD range, work group, and work item. Even though the GPU might be very useful for some program execution, the programming paradigm still is CPU-centric, and as you can see in the slide, the CPU is who has to take care of memory allocation, memory deallocation, data transfers, and kernel launch. So one question here could be, okay, I can synchronize threads that are running concurrently in the same thread block, but I cannot synchronize across thread blocks. Is there any reason for that? There might be different reasons, but one of the reasons is that this limitation in the programming model allows us to have more flexibility in the execution. This is what is called the transparent scalability. You know that not all GPUs are the same in the number of cores, right? You know that not all GPUs have the same number of cores, so they not all are so powerful. So we might have some GPUs that have, for example, nowadays, I don't know, maybe 6. I'm not going to talk about the most recent architectures yet, but maybe 2-4 years ago, what we had was the most powerful GPU that we could have was 16 shader cores. NVIDIA talks about streaming multiprocessors or SMs. We can also talk about compute units. That would be also the same. So as I said, the most powerful GPU maybe had these 16 of these shader cores, but maybe the GPUs in your laptop obviously doesn't have such a high number of SMs. So maybe they have 2, they have 4, but still we want to write our code and we want to execute our code on any GPU, right? So here you have an example. We might have a device with 2 of these cores. We might have another device with 4 of these cores, and this is our kernel. We are going to launch 8 thread blocks in our kernel. How are we going to execute these 8 thread blocks in these 2 cores or in those 4 cores? Well, maybe this way or that way. We will start scheduling thread blocks as long as there are some free slot to allocate each of these thread blocks and start executing it. As you can see, each of these thread blocks is mapped onto one of these shader core or SMs. Actually, each of the cores might handle more than one thread block, but in principle, we are going to assume that the correspondence is one thread block, one core, although you will see soon that we might have enough space to run up to 32 thread blocks in each of these cores. And the thing is that having this programming model, having this bulk synchronous programming model allows us to have this scalability and the ability to launch one particular kernel on every GPU. Question?
What core in GPU means? For example, like NVIDIA advertised they have like 3,000 or 4,000.
Yeah.
So what's that core mean?
When they talk about 3,000 or 4,000 cores, they are not talking about these cores. These shader cores contain a certain number of what they call the CUDA cores. In NVIDIA terminology, the shader core is called streaming multiprocessor, or SM. That's why I will usually say SM. And within each SM, we have the vector lanes, which are these CUDA cores, and that's what they have thousands of them. Okay? Other questions? Okay, so this is related to how the computation is organized from the programmer point of view. The programmer should take care about the thread blocks and the threads within each thread block. Let's take a quick look at the memory hierarchy, because as of now we have only talked about the GPU memory, the device memory, or global memory, which is like the standard name for it in the CUDA and OpenCL programming model. And as you can see in this slide, the host has access to this global memory. Why? Because the host should be able to move data from the CPU memory to the GPU memory and read data from the GPU memory to the CPU memory. So every time, as we said before, every time we want to offload computation onto the GPU, we need to move data to the GPU. But this is not only, luckily, this is not only the only memory that the GPU threads can use. The GPU threads can also have access to their own register file. Actually, in the previous part of the lecture, you saw how Professor Mutlu talked about the register file. This register file is partitioned, so each thread has access to its own registers. And then threads that belong to the same thread block can access to the same fast on-chip memory that is called shared memory. So it is shared because it is called shared memory because it is shared among the threads belonging to the same thread block. But a better name, and this shared memory is an NVIDIA terminology. No one really likes it. It's better to call it local memory, right? Because if this is global memory, shared memory should be called local memory. And actually, local memory is OpenCL terminology. This is a scratchpad memory. We can also talk about a software managed memory. And you will see, we will see later how to handle it. But in principle, as you can see, this shared memory will allow us to share data among these threads. It will be possible to load some important data that is in global memory into the shared memory so that it is closer to the threads. Okay? Okay. Let's take a look at the traditional program structure. I'm not going to show you an entire code. Maybe another day we will have time to do that. But essentially what you need to know today is which are the steps that we need to follow when we want to offload computation onto the GPU. So typically in our main function, in our CPU function, we are going to have several steps. Same as you need to allocate memory on your system memory, on your main memory, using, for example, malloc. You also need to allocate memory on the device memory. Allocate your arrays on the device memory. And to this end, we use one particular CUDA instruction, which is CUDA malloc, as you can see in the slide. So how many bytes are we allocating? We allocate a certain number of bytes, and we obtain one pointer that in this case is called d_in, and this is the way to allocate memory onto the GPU memory. Then we need, before launching the kernel, we need to move the data from the CPU memory to the GPU memory. And to this end, we are going to use CUDA main CPI, CUDA main copy. So in CUDA main copy, you see that we have a destination and we have a source. The H means host, the D means device, so you can figure out what's the direction, right, of this particular transfer. We are moving data from the host to the device. We will see more in detail in the next slide what's the syntax of this instruction. Afterwards, we need to define the execution configuration, essentially, as we said before, how many thread blocks do we want to launch and how many threads per block. Obviously, this is going to be related, or this is going to be dependent on the size of your data, your input or your output data, or both. And then we call the kernel. We define here the execution configuration, number of threads, and number of blocks, and the arguments. When the kernel terminates, we need to move the results, or maybe not the first kernel, maybe several kernels, because obviously we can launch several kernels sequentially onto the GPU. We will have to copy the results from the device memory to the host memory. And as you can see, this can be repeated as needed. That is, we might have an iterative algorithm, and we need to move data, compute, got results, and repeat the operation.
So if at some point we need
Exactly. That's the quartz grain synchronization. If at some point you need to synchronize this thread block with this other thread block, you need to wait until the kernel terminates and then launch a new kernel.
or if there's a shared memory access.
I mean, if the synchronization you want to do is within your thread block, you don't need to terminate the kernel. You can use this instruction, sync threads. This sync threads is intra-block synchronization. So if you want to synchronize thread 0 in block 0 and thread 32 in block 0, you simply use these sync threads. But if you want to synchronize thread 0 in block 0 and thread 32 in block 32, you need to terminate the kernel. Okay? Well, so this is essentially what it is. There are some special qualifiers. So, for example, global is the way to identify one kernel, unlike, I mean, the traditional declaration of a serial CPU function that you see on top of the slide. If we want to identify one kernel, we will use this special word, this global. And when we want to declare shared memory, we also need to use shared to identify that particular array. In principle, if within our kernel code we declare one array, this array, same as the automatic variables, will be stored in the registers. So every time you write, let's say, float A32, these 32 floats will be stored in registers, provided that there is enough number of registers. There's no enough number of registers, they will be allocated into the device memory. But we don't really need to care about that for now. Let's say these are a little bit more advanced programming hints, okay? So here in this slide, you have the complete syntax of this instructions that we presented in the previous slide. CUDA malloc is I need my pointer and how many bytes do I need to allocate. CUDA main copy, I need my destination pointer, my source pointer, how many bytes do I want to transfer from this memory to this other memory, and the direction that is defined with this word here, CUDA main copy host to device, obviously means a CPU to GPU transfer. If we want to do a GPU to CPU transfer, we will say device to host, and we can also use this CUDA main copy to transfer within the device memory. That would be device to device. This is the syntax of the kernel launch. This is for memory deallocation. And this is this explicit synchronization is an instruction we need to use in the CPU code when we want to make sure that the kernel has completed. Why is that? Because actually the kernel launch is asynchronous. And this is good because the CPU thread can launch the kernel and start doing different things. So it's good that the kernel launch is not blocking. It's good that the CPU can do different things while the kernel is running on the GPU. But at some point, the CPU might need to use some results that the GPU has produced. And if we want to make sure that the GPU terminated the kernel, then we need to use the CUDA device synchronize. Actually, we don't always use this CUDA device synchronize because, not always, because also the CUDA main copy is blocking. So if we have a kernel launch and right after that we have a CUDA main copy, we don't need to use this CUDA device synchronize. But this is not the only way to transfer data from the CPU to the GPU or from the GPU to the CPU. This CUDA main copy is blocking, so every time the CPU executes this main copy, it is blocking. But there is also some asynchronous copies that we will see in the end of this part of the presentation. And they are also very useful. So in these cases, we really need to use this CUDA device synchronize at some point. Okay, let's take a look at how we are going to index our data elements within the kernel. And just as an example, we are going to use the image layout. You already know that images are composed by hundreds or thousands of pixels, and they are typically allocated in a row major layout. You already know that. We are going to see how we can access these pixels that belong to an image using our threads, because actually this is important and for beginners, for programmers that they start programming in a massively parallel language like CUDA, in the beginning might be a little bit difficult to go from the sequential concept of programming to a parallel programming where you have to care about the indices of many threads that are running in parallel. So, well, this is how we access any pixel in the image. For example, this pixel here is image 01. This pixel here is image 12. But actually, as you know, this is laid out in a row major layout in the memory. So each row of the image is after the previous row. We have something like this. So actually, when we want to access pixel 01, what we are accessing is this memory address, 0 times 8 plus 1, being 8 the width of the image, right? So let's see how we do that when we have many parallel threads. Remember that we have a block, well, we have a grid, and this grid is composed by several blocks, and in each block we have a certain number of threads. So there are some predefined built-in variables that are the grid dimension and are the block dimension. Obviously, this is defined by the programmer when we launch the kernel. So within the kernel, we can use the number of thread blocks that have actually been launched. This is the grid dim, the dimension of the grid. And we can also use this block dim, which is the dimension of the block, that is the number of threads within the block. We also have or block index and or thread index. Actually, we don't need this. So I'm going to remove it. Okay, so in order to index each of the thread blocks, we are going to have one block index. In order to index each of the threads within a thread block, we have one thread index. In principle, in this example, we are going to see a one-dimensional thread block and a one-dimensional grid. You will see next that it's possible to have 2 or 3 dimensions as well. So, for example, in this case, we want to perform some computation on this image, and this is massively parallel, so we know that we can have one thread working on each of the pixels of the image. You already know that these threads are organized into thread blocks, so we are going to see in this slide how we distribute these pixels among threads and among thread blocks. So block 0 will take care of these 4 pixels here. The next block can take care of the next 4 pixels, and so on. So if we take a closer look at block 0, we will see that we are going to have 4 threads executing some operations on each of the pixels that have been assigned to this particular thread block. So now we are going to see how we have to index each particular pixel using our thread block index, block idx.x, and our thread index, thread idx.x. So in this case, if we want to access one particular pixel, we need to make use of the thread block index, the block dimension, and the thread index. So this pixel, for example, is in block index equals 6. You see block is 0, 1, 2, 3, 4, 5, 6. And within block 6, it's the first thread. It's first number 1. It's 0, 1. So this is the way we can access this pixel number 25, okay? So in a very similar way, we are going to do that for 2-dimensional blocks. When we have 2-dimensional blocks, or we have a 2-dimensional grid, we are going to use 2 indices, x and y. And when we launch the kernel, we not only define how many thread blocks we want to launch, but also how many thread blocks in each dimension. For example, in this particular case, for this image, we are going to launch grid dim x equal 4 and grid dim y equal 4, right? So how are we going to access the pixels in this particular case? Well, for example, here on the right of the slide, you see the pixels that are assigned to one of the thread blocks. This thread block is going to be block x equal to y equal 1. And now, within the thread block, we also have a 2-dimensional organization of threads, and that particular one is thread x equal to 1, y equal to 0. How are we going to access our pixels now? Well, we need to calculate the row and the column. That's the first thing we have to do, to calculate the row of the column for each particular pixel. So first, if we want to calculate the row, we need to use the block index y, and we need to take the block dimension in the y direction into account. So for example, this pixel here is in block 0, 1 in the y dimension, and within the thread block, it is going to be accessed by one thread that has thread index y equal to 1. So that's the way to calculate the row. The way to calculate the column is similar, but using the x indices. So it's simple, right? Okay. So these are the built-in variables that the programmer needs to use in the code when you want to access some particular data element from some particular thread in some particular thread block. Okay, before going further, let's take a quick look, or let's briefly review the GPU architecture. You have already seen, you're already familiar with the GPU architecture. Now what I want to do here is just to reinforce a little bit the concepts you have seen in the previous part of the presentation, and also take a look at a newer architecture. So this is the typical organization of the GPU. The GPU is composed by a streaming processor array that is composed by something called TPCs, texture processing clusters, or something like that. That concept is not important for us. The important thing for us is that within each of these TPCs, we might have 2, 3, or 4 SMs, which are the shader cores, okay, or the compute units. We can also talk about compute units. So in each of these shader cores, or SMs, this is essentially what we have. As you can see, the picture is very similar to what you saw in the first part of the presentation. And this corresponds to the oldest CUDA architecture that contained only 8 of these vector lanes. So these are the SPs, or CUDA cores, okay? So remember that you asked about you asked about that slide in particular. We had 32 threads in a warp, and we need to execute these 32 threads on top of these 8 cores. We don't have 32 cores in this case. We have 8 cores. So how are we going to do that? We are going to schedule 8 threads in one cycle. So that's why it was represented that way in that slide. But this is, as I said, the oldest architecture. This is, for example, a newer one. This is the NVIDIA Fermi architecture. And as you can see here, we have 32 cores in total, but actually only 16 of these cores are going to be used by one single warp. So here, what we need is 2 cycles to schedule the entire warp on each of these groups of 16 SPs. How do we connect the programming model, the threads and the thread blocks, to the hardware? It's as simple as dividing the thread block into warps. So remember in the beginning that I said, do you know what are going to be the typical thread block sizes? And I told you it's going to be a multiple of 32. Why is a multiple of 32? Because every time a thread block is scheduled on one SM, or one shader core, the thread block is decomposed into a certain number of warps, and each of the warps has 32 threads. Okay? It's clear? Okay. Is it clear? Okay.
So why one warp only has 32 threads? How is the number 32 defined? Why not 60?
So why do they decided to make the warp size equal to 32?
Yeah.
I don't know. So
Across whole architecture or that
So the 32 is the size in NVIDIA architectures, in all NVIDIA architectures so far, same as it is 64 in AMD architectures. AMD is 64. What they call the waveform is 64. Maybe in the future it might change, you know, but for now it has always been 32. Typical values, typical sizes of the thread block are 64, 128, 256. So these are typical values, actually. In this slide, what you can see is also typical numbers for SMs and for SPs, so how many cores within each of these shader cores, or how many vector lanes within each of these shader cores, and how many SMs or shader cores in total. So as you can see, this has been changing over the last decade, and now the two more recent generations, Pascal and Volta, already have increased the number of SMs. They are much powerful nowadays. By the way, I also want to point out two differences between, something that is related to the evolution of these SMs. As you see here, in this SM belonging to the G80 or Tesla architecture, you have 8 of these SPs and also have 2 SFUs. The SFUs are special function units. They are intended to, they execute some transcendental operations like sine, cosine, and these type of operations. They still exist in the Fermi architecture, which is newer. You see that we have 4 in this SM. But also look that we have these new units that are LDST, so they are load stored units. They take care of address calculation for memory accesses. So this is why in the previous part of the lecture, Professor Mutlu said that these GPUs are kind of combination between vector processors and array processors, because we not only have several vector lanes, but also we have different types of lanes, okay? Also, if you look at the top part of the streaming multiprocessor, you will see there the instruction cache and the warp scheduler, which are these units that take care of fetching the instructions and issuing the instructions on the available cores. Okay, so now let's talk about the performance considerations. As I said in the beginning, there are two main bottlenecks. One of them is the data transfer. This is an inherent bottleneck. We cannot avoid that, at least in the discrete GPUs, because we need to move data from the CPU memory to the GPU memory, and we need to move the results from the GPU memory to the CPU memory, and also the global memory access. Actually, when we talk about these optimization techniques or these performance considerations that we are going to talk about, you will see that most of them, or an important part of them, are going to be focused on improving the memory access in general. So the first thing we will talk about is the latency hiding mechanism that has also been introduced in the previous part of the lecture. Essentially, this is based on the fine-grained threading model and the fact that we have warps and we can schedule these warps so that we can be executing warps while we are doing some other operations that are longer latency. And we will also talk about how to more efficiently access the memory. this is what we call the memory coalescing. Next, we will talk about the shared memory we have already introduced, and in which cases the shared memory is going to be really useful, and how to access this shared memory, because this is a banked memory or an interleaved memory, so it is possible that we have bank conflicts, as it was described, for example, in yesterday's lecture. We will talk about the SIMD utilization that has also been introduced before, but you will see some code examples here. Also, an important source of bottlenecks, which are the use of atomic operations. And finally, we will finish with the data transfers and explore a little bit how it would be possible to optimize these data transfers by doing some overlap of the computation and the communication. So for the latency hiding, as I said, what we are going to exploit is the multi-threaded architecture, the multi-threaded execution, the fact that we have many warp or several warps running at the same time in each of these shader cores, and the fact that we are able to issue one of these warp instructions every cycle. So here you have like a very simple toy example. Assume that we have 4 active warps in one SM, and at some point, each warp needs to execute a long latency operation. What is a long latency operation? For example, a memory access, okay? Also, for example, the special function units also take longer than regular vector lanes, right? But the memory accesses are especially critical because they take hundreds of cycles, as you know. So how can we hide this long latency of instruction 4, which is a memory access, by executing other warps in the meantime? So that's how we can hide this long latency. If our available warp level parallelism or thread level parallelism is not as high, we will have some gap, and at some point we will see that the effect of that long latency instruction on the performance. So essentially what we need to know, what we need to do here is ensuring or try to ensure that the number of active warps that we have in each SM is high enough to hide these long latency instructions. The number of active warps is what is called the occupancy. Actually, the occupancy is defined as the ratio of active warps to the maximum number of warps, okay? And unfortunately, the number of warps that are going to be executed on one SM or one shader core is not something that the programmer can arbitrarily choose. This is dependent on the use that the threads and the thread blocks make of the available resources. Actually, this depends on 4 important resources. The first of them is the maximum number of warps that can run on an SM. Why do you think this maximum number of warps that can run on an SM is limited? Well, because we have, for example, a maximum number of program counters. Remember from the previous part of the lecture that each warp has its own program counter. So in current architectures, for example, we have 64 of these program counters. So we can just run up to 64 warps. Another limitation is the maximum number of blocks per SM. Remember that in the very beginning I said, let's assume that each of the thread blocks is mapped onto an SM, onto a shader core, but actually more than one block can run on each SM. How many? Up to 32. Then, within each SM, as you saw in the previous slide, we have some registers that are going to be partitioned among the threads that we are going to execute. The register size in current architecture is the 256 kilobyte or 64K 32-bit registers, and also the available shared memory. So this shared memory is 64 kilobyte in the most recent architecture. So what's the usage that one particular kernel needs to do of these resources? This is what is going to condition the maximum number of warps that we can execute in our program. Just let me, just in case this is not completely clear, just let me give you an example here. So we know that in our, like this, kernel, in our kernel launch, we want to launch a certain number of blocks, and each block is going to have a certain number of threads, right? And here we have our arguments, okay? Then, in other file, we will have our global, which is our kernel, or global function, or kernel. And in this kernel, you already know that we are going to use, for example, the block index, and also the thread index. Oh, yeah, sorry. Okay, now it's okay. So also these threads that are going to execute this code need to share data for some reasons. We haven't talked about that yet, but we will talk next. So maybe these threads that are going to execute this code, or these threads that belong to one particular thread block, are going to use some shared memory. Let's call it A, and this shared memory is, I don't know, 128. Okay? So in this particular case, how much is this is, let's say, int. So how much is 128? 128 times 4 is 1024 bytes, right? So now, if we go back to the slide, you see each of our thread blocks needs 1 kilobyte, needs 128 bytes. So how many thread blocks could we execute in one SM if in each SM we have 64 kilobyte? Up to 64, right? So our occupancy, in this case, is not going to be limited by the shared memory, right? Is it going to be, it might be limited by some of the other three factors. Which one? At least by the maximum number of thread blocks, right? So maybe we need to, I don't know, maybe much more than that. 6,128. So in that case, more or less, we could run up to actually 64, I would say 2 or 3, right? Thread blocks. Also, this is explicitly coded by the programmer. It's the programmer who has to say how many bytes do I really need, or how many elements do I really need here. But then here we will have many instructions. For example, int a equal 4, and maybe we have a for loop here. So here, the compiler will also find that we need a certain number of registers to execute this code. Okay? So that will also be a limitation. It's always possible for us, if we want to calculate the occupancy of one kernel, the occupancy of the SMs, it's always going to be useful to use the appropriate compiler flag that will tell us what's the registers and the shared memory needs. Oh. So as you see, it's quite a simple calculation, but it's important to keep these numbers in mind in order to maximize as long as possible the occupancy, because this occupancy defines the available thread level parallelism or the warp level parallelism and defines the ability of the GPU to hide long latency operations as the global memory accesses are. These global memory accesses, you already know that they take hundreds of cycles. They are very long latency operations, but it can be even worse. And it could be even worse in case we don't access the memory in the appropriate way. In order to have the most optimized, the most efficient memory accesses, we need to coalesce. We need to have coalesced memory accesses. And what is a coalesced memory access? A coalesced memory access essentially means that the 32 threads that belong to a warp access the data elements that are in one cache line. Typically, the cache line size is 128 bytes. So this corresponds to 4 bytes per thread. So if we want to have the most efficient memory access that is possible, we need to try to do that. In a more simplified way, we could say that consecutive threads should access consecutive memory locations, but it's not necessary that it's as strict like that. They could be accessing different elements in the same cache line, but this will be the way to have the most optimized access to the memory. And this is what you have in this right picture on the here. So this arrow represents the data elements that are accessed by the threads in successive iterations. So for example, here we have 2 threads. If thread 0 accesses here and thread 1 accesses here, they both are accessing consecutive memory addresses that belong to the same cache line. So these memory addresses, this cache line, can be retrieved in one cycle, let's say. In the next iteration, these 2 threads access the next element, and then the next element, and each of these accesses will be a coalesced access. But what if we want to access the row this way, the data elements this way? We have this thread 1 here, thread 2 here. What will be the problem? The problem is that they are performing an strided access. So we will have thread 1 here, we will have thread 2 here, and in the middle there are a lot of data elements that we are not accessing. And depending on this width, these 2 elements might be very far from each other. Let's take a closer look at this in the next 2 slides, and then I will also show you an example in the paper. So for coalesced accesses, on top of the slide, you have one matrix, and as you know, this matrix is in a row major layout, so it's stored row after row. If all threads are going to access, each thread is assigned 1 column of the matrix, and they are going to access yellow, red, blue elements in the successive iterations, we will have threads 1 to 4 accessing 4 elements that are consecutive. So this is a coalesced access, and these, in this case, 32 elements can be loaded from memory in one step. In the second iteration, we have the same 4 threads accessing the red row, and again, we need one single step, we need one single cycle to access these 4 elements. However, if we want to access the threads by row, we want thread 1 access the yellow row, thread 2 access the red row, and so on. We have thread 1 accessing the first element in the yellow row, while the thread 2 is accessing the first element in the red row. And there is might be a huge stride between them. Probably they will belong to different cache lines. So the problem here is that we need 2 memory accesses, or in this particular example, we will need 4 memory accesses to get all the data that the 4 threads need in each particular iteration. Okay? Actually, this also entails or imposes a preferred layout for the data. So this is why we talk about 2 different possible layouts. Every time, the example in the previous 2 slides was with a matrix, but sometimes we are going to use structures, and each of the structure might have several elements. So how are we going to organize our data? That will depend on how the threads are going to access that data, right? In the typical 2 organizations or 2 layouts are the structure of arrays and the array of structures. So you see what's the difference between them. In the array of a structure, which probably it's a better deal for CPUs, we are going to have an array, and each of the array elements is a struct. In this case, 3 floats and 1 integer. As you know, this array of structures is laid out in memory, like this part, like in this picture that you have in the slide. But probably this is not going to be a good deal for the GPU. Why? Because if we assign each of these structures to each of the threads of the GPU, in one particular iteration or one particular access in our GPU code, we will have thread 0 accessing this blue element, thread 1 accessing this blue element, thread 2 accessing this blue element. And as you see, this there is a stride between these blue elements. So it is likely that these elements belong to different cache lines. So the problem is that we will need 1, 2, 3, 4, many more memory accesses to get each of these blue elements that we need in the first part of the kernel, for example. However, if we use a structure of arrays, something like the layout that you see in the top of the slide, we can have, if in one particular point in time, or consecutive threads or threads belonging to the same warp or belonging to the same thread block need to access the blue elements, they will be doing accesses to consecutive memory locations. So we will need just one single memory access for each warp. So that's why the performance will be actually much higher. In the next slide, indeed, what you have is a comparison for simple micro-benchmark. Actually, these results have been obtained with a micro-benchmark with an access pattern, as the one I described in the previous slide. Depending on the structure size, depending on the slide, your throughput can be very high, very good, or can be very, very low. As you can see in the slide. This is for the GPU, but, however, for the CPU, the array of a structure is not a bad idea. Actually, usually for CPUs, this organization is not bad because you know that CPUs have big caches that can store many of these structures, many of these elements. So every time we access here, for example, the blue element, we will also be bringing the rest of elements in this structure and probably many more to our caches, so they will be available in the successive iterations, in the rest of the code. This but these results have been obtained on an AMD Kaveri. It's an integrated CPU plus GPU system, so we have the same. We have both devices in the same chip. So that's why I think it's interesting to compare how the performance might be very different depending on how the data is organized and depending on which size we are accessing that data. Okay. So let me also give you one more example here and talk about an important operation in current GPUs, because you know that GPUs have become very popular in the recent years, but even more in the last 2-3 years, because they are essential to accelerate these deep neural networks that now are going to solve every single problem in the world. And the truth is that these deep neural networks are based on matrix multiplication. I don't know if you are very familiar with that, but essentially they can be converted. The computation necessary in each of the convolutional layers or recurrent layers can be easily converted into matrix multiplications, and this is why they can be very good accelerated by GPUs. NVIDIA, for example, has the cuBLAS library, and the cuBLAS library has super optimized matrix multiplication. Actually, it is so optimized that it almost reaches the peak throughput. So if your peak throughput is 1 teraflop, probably with cuBLAS matrix multiplication, you can reach 900 gigaflop or something like that. So it's super optimized. One of the reasons is because they directly code in assembly language. So they don't even use CUDA for this super optimized implementation. But let me quickly explain you how this is implemented. So usually when we want to do a matrix multiplication, we have something like that, right? Matrix A times matrix B equals C. You know that this is matrix A is M times P, matrix B is P times N, and that's why C is M times N. So if this is our matrix C, this is M, the number of rows, this is N, the number of columns, and here this is, this is supposed to be the same width, right? Okay, I'm adding an extra column. I'm padding a little bit. So this is P, this is N. So this is our matrix B. And here we have matrix A. This is M, and this is P. So, okay. So how do we map the computation that we have here in our matrix multiplication onto those thread blocks and threads we have been talking about? Well, the most optimized implementation of matrix multiplication actually assigns each of these elements in matrix C to each thread. So for example, this element here is going to be computed by thread 0. Thread idx.x equals 0 and thread idx.y equal 0. Okay? So observe that this thread needs to access this entire column, because obviously to calculate this element we need to perform the dot product of this column and this row, right? And now this element will be computed by tx equal 1, ty equals 0, okay? So observe that there are different ways to access these two A and B matrices, right? For matrix B, probably we will have an efficient access if we just make these consecutive threads access these consecutive memory locations. So our thread 0, 0 will be here, or thread 0, 1, or actually 1, 0 will be here, or thread 2, 0 will be here. They are accessing consecutive memory locations. They are accessing memory addresses that are in the same cache line, right? However, what will be these guys accessing in matrix A? Well, that's a good question. One thing we could do, and actually what we have to do, is having them all accessing this element. Because the first thing we have to do is multiplying this element with this element here, or this element here, or this element here, right? But observe that there is a problem here. We are going to have all these consecutive threads accessing the same element, right? Is that efficient? Well, it might be coalesced, but actually we are going to have 32 threads accessing one single element. So probably we could do it better, right? Another possibility would be to assign the threads like this. I mean, instead of saying this is thread 0, 0, and this is thread 1, 0, we could do the other way around. We could say this is 0, 0, but this is 0, 1. But in that case, the problem is going to be that we are going to have accesses like this. And remember that this entails that we have a stride between these two threads. So such a stride means an uncoalesced access, so that means it's inefficient. How are we going to handle with that? Well, this is a good moment to introduce the shared memory. Because observe that these two threads that are going to calculate these two elements, in their first iteration, they need to access this and this, but they both need to access this, right? So what we can do is, before performing this computation, what we can do is loading some of these elements into a faster memory called the shared memory. Okay? So actually, as you see, this is a two-dimensional organization. What we have here is a two-dimensional organization of thread blocks. So these 4 elements of matrix C are going to be assigned to bx0, by0. And what these 4 threads here are going to do is accessing these elements, but when they have to access this matrix, the first thing they will do is loading one entire tile of this matrix into the shared memory. And the shared memory is a much faster memory that can be accessed in, let's say, less than 1/10 of the cycles that the global memory, and that's why we can importantly accelerate the execution of this operation. Let's take a look at an example. What time is it? Okay, we still have 10 minutes. Let's take a look at an example of this, even with a more simple case, which is some filtering operation. This is just a Gaussian filtering, right? This corresponds to a Gaussian filtering. We have our image, and what we have to do is applying one mask on top of each pixel, and actually the computation simply consists on something like that. For that particular pixel that is in green, we need to access the pixel itself and the pixels in the surroundings, and multiplying each of the pixels to certain value of the mask and accumulate, okay? And this will be the output for that particular pixel. This is essentially a convolution, right? So observe that in this case, if we assign each of the pixels to a different thread, threads that are neighbors are going to access many pixels that are also accessed by their neighbors, right? So for example, you have the green pixel there, but the one on the right shares with these green pixels how many of the surrounding pixels? Up to 6, right? So what we could do here is define some tiles, and each of these tiles is going to be loaded into the shared memory so that they are closer to the cores, to the these SPs or CUDA cores that we have within each of the shader cores, and we can have a much faster access to them, right? For them to do this, we need to declare our shared memory, and then we will have to load. We don't have the details of how to load, but essentially we will have to have our threads, the threads in our thread block, go into the global memory, reading each of these pixels and storing them into this array. And then we will need to synchronize to make sure that all the reads and write into shared memory have completed. And afterwards, we will execute this computation using the data that is stored in the shared memory. Okay? So that's why the shared memory is so useful for every single operation where we have, or every single kernel where we have data reuse, as the example of the Gaussian filtering or the example of the matrix multiplication that you saw before. The only problem with the shared memory is that, as I said before, it's an interleaved memory. So we have banks, and as we have banks, we might have bank conflicts, right? So here, how many banks do we have? We have 32 banks. The way the words, the addresses are mapped onto the banks is defined by this expression that we have here. So we are using the lower 5 bits of the address to go to the particular bank, and obviously we can have bank conflicts, and as you can see in this slide, okay, this is for assume a warp of 16 thread instead of 32. This, if we have a linear addressing, we have we won't have bank conflicts, as you can see. We will also have a random addressing, but if no two threads access the same bank, we also have maximum throughput. But we can also have bank conflicts. And when do we have bank conflicts? When we have strides. Remember that if we have 32 banks, which is a power of 2, if we access with strides that are power of 2, we will have bank conflicts, right? In this case, our stride is 2, so we have a 2-way bank conflict. Or if our stride is 8, we have an 8-way bank conflict. How can we avoid these bank conflicts? In the yesterday's lecture, actually, Professor Mutlu explained that one possibility was using hash functions, right? Hash functions are Well, if this is implemented in hardware, it's okay for the programmer. If it's implemented in software, it's not so okay, because actually you have to care probably about what hash function you need to find for your particular access pattern, right? So a much simpler optimization can be using padding. What is padding? Padding, you know the meaning of padding, right? Padding essentially means that we are going to pad some shared memory locations that actually we are not going to use. Remember this tile that we have here. How is this mapped onto the memory? Well, let's take a look at our shared memory. Can be something like this, right? We will have 32 banks, from bank 0 to bank 31. This is bank 1, this is bank 2, and so on. So if our access to the shared memory is something like this, we have a linear stride. Stride is equal to 1. We will have the maximum throughput, because thread 0 access here, thread 1 here, thread 2 here, and we can be accessing the 32 threads, the 32 banks at the same time. But in case we have a stride, for example, for simplicity, let's consider a stride equal 32, we will have thread 0 here and thread 1 accessing here, right? So that's a bank conflict. And actually, it's a 32-way bank conflict, because thread 2 will access here, thread 3 here, and so on. What can we do to simply avoid this? We can pad. Instead of having the data stored like this, we could have something like this. This is bank 0, 1, 2, 31. We store the first row in these first 32 positions, each of them in one bank. And then for the second row, we are not going to use this element. So this memory location. So this element here now is going to be stored here. Okay? So even though our stride is 32, or should be 32, actually now our stride is going to be 33, because we are padding one position, right? In this row, our padded position is going to be this one. So if we have thread 0 here, thread 1 here, now we are going to have thread 0 here, thread 1 here, thread 2 here, and so on. So we avoid the bank conflict. This is a very simple way to optimize the shared memory access. Okay, it's only 3 minutes to finish, but I want to very quickly go through the next topic, which is the SIMD utilization, the branch divergence, or the intra-warp divergence. And even though in some cases this is not avoidable, in some other cases it might be, right? You remember from the previous part of the lecture that we might have if-else statement, and some threads of the warp might follow one path and other threads follow a different path. You know that already this relies on the use of a mask or predicated instructions, right? Well, this is a divergence divergent execution. However, we could try at least to change our code to do something like this. Instead of having even threads going through one part of the computation through the if, and the even odd threads going through the else part, we could have the lower part of our thread block going through the if, the higher part of our thread block going through the else. A very good example for this is vector reduction. So vector reduction is essentially adding up all the elements belonging to one vector. So one naive implementation for this could be something like that. We could use even threads to compute the addition, in this particular case, the addition of two consecutive elements, as you can see in the slide. What's the problem with this naive mapping or this naive implementation? The problem is, as long as iterations pass, we have less threads running, but that's not the problem, because actually that's inherent to the algorithm itself. The problem is that here we only have even threads working and odd threads are idle. So half of our warp is completely idle. So we are wasting half of our vector lanes, right? This naive mapping corresponds to this code that you can see here. So these are the iterations, and in each iterations we multiply the stride by 2. The stride is exactly the element that we are accessing in the beginning. In the first iteration, the stride is 1. In the second iteration, half of the active threads retire, and the other half access stride 2. In the third iteration, they access with a stride 4, and so on, right? So one way to do exactly the same thing, but in a more efficient way, is something like this. Keep in mind that this is vector reduction, and if we are performing an addition, it's not important the order in which these additions are performed, right? So we could have a mapping like this. Observe that in this case, we are going to have consecutive threads active, and each of the threads is reading one position and another position that is far away. But the good thing here is that the next thread is also active, and it's also reading another position that is far away, but it's also consecutive to the adjacent thread, okay? This is a very simple transformation, as you can see. And, well, maybe you can take a closer look at the code and completely understand it. But what I just want to state here is that even though divergence is always going to exist and it's a problem in SIMD architecture and GPU architectures, it's also for the programmer possible to try to optimize how these memory accesses are, or how this computation is performed, and obtain a much higher performance. We are going to finish here. Thank you very much for your attention. I hope this was interesting for you. We can still talk about that every time you want, and probably in the future we will have time to finalize this presentation and maybe talk about more advanced topics. Thank you, guys.